In this video, we're going to continue talking about trees, and in particular, look at walking a tree or visiting the elements of a tree or traversing the elements of a tree. So often we want to go through the nodes of a tree in a particular order. We talked earlier when we were looking at the syntax tree of an expression, how we could evaluate the expression by working our way up from the leaves. So that'd be one way of walking through a tree in a particular order so we could evaluate. Or another example might be printing the nodes of a tree. If we had a binary search tree, we might want to get the elements of a tree in sorted order. There are two main ways to traverse a tree. One is depth first. So there, we completely traverse one subtree before we go on to a sibling subtree. Alternatively, in breadth first search, we traverse all the nodes at one level before we go to the next level. So in that case, we would traverse all of our siblings before we visited any of the children of any of the siblings. We'll see some code examples of these. In depth first search, so we're going to look here at a in-order traversal. And that's really defined best for a binary tree. So this is in-order traversal is what we might use to print all the nodes of a binary search tree in alphabetical order. So we're going to have a recursive implementation where if we have a nil tree, we do nothing. Otherwise, we traverse the left subtree and then do whatever we're going to do to the key, visit it. In this case, we're going to print it. But often there's just some operation you want to carry out and then traverse the right subtree. So let's look at an example of this. We've got our binary search tree and we're going to look at how these nodes get printed out if we do an in-order traversal. So to begin with, we go to the less node. And from there, since it's not nil, we're going to do an in-order traversal of its left child, which is Kathy. Similarly, now we're going to do an in-order traversal of its left child, which is Alex. Okay. We do an in-order traversal of its left child, which is nil, so it does nothing. So we come back to Alex and then print out Alex, and then traverse its right subtree, which is nil and does nothing. We come back to Alex, and then we're finished with Alex, and we'll go back to Kathy. So we have successfully completed Kathy's left subtree, so did an in-order traversal of that. So now we're going to print Kathy and then do an in-order traversal of its right subtree, which is Frank. So we go into Frank. Similarly, now we're going to print out Frank. We finish with Frank and go back to Kathy. And now we've completed Kathy totally. So we go back to Les. We completed Les's left subtree, so we're now going to print Les and then traverse Les's right subtree. So that is Sam. Traverse its left subtree, which is Nancy, print it out. Go back to Sam. We've completed Sam's left subtree, so we print Sam. And then go ahead and do Sam's right subtree, which is Violet, which will end up printing Tony, Violet, and then Wendy. We're completed with Wendy. We go back to Violet. We've completed her right subtree. So we go back to Sam, completed his right subtree, go back to Les, completed his right subtree, and we're done. So we see we get the elements out in sorted order. And again, we do the left child, and then the node, and then the right child. And by our definition of a binary search tree, that then gives us to them in order, because we know all the elements in the left child are in fact less than or equal to the nodes itself. The next depth first traversal is a pre-order traversal. Now, the in-order traversal really is only defined for a binary tree because we talk about doing the left child and then the node and then the right child. And so it's not clear if you had, let's say, 3 children, where it is you'd actually put the node itself. So you might do the first child and then print the node and then second and third child, or first child and then second child and print the node and then third child. It's kind of undefined there, so not well defined. However, these next two, the pre-order and post-order traversal, are well defined, not just for binary trees, but for general arbitrary number of children trees. So here the pre-order traversal says, we're going to go ahead, first if it's nil, we return. We print the key first, that is, we visit the node itself and then its children. So we're going to, in this case, go ahead and go to the less tree and then print out its key and then go to its children. So we're going to first go to its left child, which is Kathy. And for Kathy, we then print Kathy, and then go to its left child, which is Alex, print Alex. We go back to Kathy, and we've finished its left child, so we now need to go to its right child, which is Frank. We finished Frank, we finished Kathy, we go back up to Les. We've already printed Les. We've already visited or traversed Les's left child. Now we need to traverse Les's right child. So that'll be Sam, which we'll print out, and then we'll go to Nancy, which we'll print out. We'll go back up to Sam and then to Violet, and we will print Violet, and then print Violet's children, which will be Tony and Wendy. And then return back up the tree. A post-order traversal is like a pre-order traversal, except instead of printing the node itself first, which is the pre, we print it last, which is the post. So all we've really done is moved where this print statement is. And here then, what's the last of these nodes that's going to be printed? Well, it's actually going to be Les, because we're not going to be able to print Les until we've finished completely dealing with Les's left subtree and right subtree. So we'll visit Les, and then visit Kathy, and then Alex, and then we'll actually print out Alex. Once we're done with Alex, we'll go back up to Kathy and down to Frank, and then print out Frank. And then once we're done with both Alex and Frank, we can then print Kathy. We go back up to Les, and we now need to go deal with Les's right child, which is Sam. In order to deal with Sam, we go to Nancy, print Nancy, go back up to Sam and down to Violet, and deal with the Violet tree, which will print out Tony, and then Wendy, and then Violet. And on our way back up, then, when we get to Sam, we have finished its children, so we can print out Sam. When we get up to Les, we finished its children, so we can print out Les. One thing to note about the recursive traversal is we do have, sort of under the covers, a stack that's being used, because in a recursive call, every time we make a call back to a procedure, we are invoking another frame on the stack. So we are saving implicitly our information of where we are on the stack. Breadth first, we're going to actually use a queue instead of a stack. So in the breadth first, or we're going to call it level traversal here, we're going to go ahead and instantiate a queue, and on the queue, first put the root of the tree. So we put that in the queue, and then while the queue is not empty, we're going to dequeue, so pull a node off, deal with that by printing it, and then if it's got a left child, enqueue the left child. If it's got a right child, enqueue the right child. And so this will have the effect of going through and processing the elements in level order. We'll see the example here, and we're going to show the queue. So here, let's say we're just before the while loop, the queue contains Les, and we're going to now dequeue Les from the queue, output it by printing it, and then enqueue Les's children, which are Kathy and Sam. Now we visit those in order. So first we're going to dequeue Kathy, print it out, and then enqueue its children. Remember, when we're enqueuing, we go at the end of the line, so Alex and Frank go after Sam. So now we're going to dequeue Sam, print it, and then enqueue its children, Nancy and Violet. So we can see what we've done then is we first printed Les, that's level 1, and then we printed the elements at level 2, which are Kathy and Sam. And now we're going to go on to the elements at level 3. So notice all the elements in level 2, level 3, Alex, Frank, Nancy, and Violet, are in the queue already. And they're going to all be processed before any of the level 4 nodes are processed. So even though they'll be pushed in the queue, since the level 3 nodes got there first, they're going to all be processed before we process any level 4 ones. So here we dequeue Alex, print it out, and we're done. Dequeue Frank, print it out, we're done with Frank. Dequeue Nancy, print it out, and we're done with Nancy. And Violet, we print it out, but then also enqueue Tony and Wendy, and then dequeue those and print them out. So this is a breadth first search with an explicit queue. You can do depth first searches rather than recursively, iteratively, but you will need an additional data structure, which is a stack, in order to keep track of the work still to be done. So in summary, trees are used for lots of different things in computer science. Okay? We've seen that trees have a key and normally have children, although there are alternative representations of trees. The tree walks that are normally done, or the traversals, are DFS, depth first search, and BFS, breadth first search. There are different types of depth first search traversals: pre-order, in-order, and post-order. When you work with a tree, it's common to use recursive algorithms, although note that we didn't for the breadth first search, where we needed to go through the elements of the tree in kind of a non-recursive order. And finally, in computer science, trees grow down.